Vision is the transduction of light within the visible spectrum into neural signals. There's really nothing special about our visible spectrum. If you've ever taken a physics class, you'll know that the electromagnetic spectrum is very extremely large, and the visible part of it is super, super tiny. Now, that super tiny area in between ultraviolet and infrared, that super tiny area, like I said, that's not terribly special. It could have been over here, it could have been over there, it's just it happens to be here for humans. And when I say here, I mean in between about 400 nanometer wavelength and 700 nanometer wavelength. So that's what the human visual spectrum is, but it's not the same for all animals. If you weren't aware of this, many insects, some reptiles, and even some animals can see in the ultraviolet range. So when they are, going around looking for flowers or whatever, they see patterns, they see colors that are imperceivable. There's no possible way we could detect it unless we use ultraviolet imaging equipment. So for many bees, for example, they can easily detect flowers because those flowers pop out from the green background. Those flowers are really bright and colorful compared to, all the other foliage. And then you could go in the other direction too. Some animals can see into that infrared range. Like a lot of reptiles, including snakes, can see some infrared light. And that infrared light is oftentimes, produced by warm little fuzzy mice. So that heat, heat vision basically allows snakes and other reptiles to hunt effectively when there isn't much light being produced in the environment. So they can hunt very well at night. But many animals, actually, especially most mammals, don't have as good a vision as humans. So not only can they not see as clearly, but they also oftentimes can't see as many colors. Take dogs, for example. Dogs can detect some color, just not as much as we can. All they can really detect is blues and yellows, mostly. So they have a restricted kind of visual spectrum. But before we really get into any specifics about human vision, I just want to mention a few important terms. So you have hue. Hue refers to those basic color categories. So what wavelengths of light we're talking about, that's the hue. Saturation, that's the degree to which the light wavelengths are pure or mixed. So what I mean by that is, when you take any image, you're getting all different kinds of light. So you're getting some of the high wavelengths, some of the low wavelengths, and so on. But if you separate out those and you have only a single narrow band of light coming from an object, that object will look very, very colorful. It'll look very, yellow or blue or red. But when you start mixing all the light together, it kind of gets whitish or gray. And then you have brightness. So brightness refers to the perceived intensity of the light being emitted from an object. But brightness, hue, and saturation are all subjective. So all of these things are going to be affected by the context. There are more objective ways to detect light. Like you can get specialized equipment that you can use to scan. It looks like a little light gun thing. It will scan the light that you're aiming it at and tell you the wavelength, the amplitude, and so on. But of course, as humans, we don't do that. We're much more influenced by the context. So I'll talk a lot about that in just a little bit. But before I do, I just want to explain a little bit more about what kind of vision humans have in comparison to other animals. So our field of view is pretty typical for carnivores. When you look at all the carnivores that live on this planet, what you'll see is they tend to have two forward-facing eyes. The classic example would be an owl. An owl has two forward-facing eyes. So the consequence of this is that you have a restricted field of view. I can't see anything behind my arms. So everything that happens around back here, I'm completely blind to. But despite all that missing information, I do have excellent depth perception. When you have two eyes that overlap like this, that allows you to see exactly how far away certain things are, like a tasty little mouse or something like that. Now, herbivores, on the other hand, they tend to have lateral facing eyes. So they have eyes that kind of point out in different directions. There isn't any overlap in their two fields of view, or if there is overlap, it's very small. So they have a very wide field of view. Some herbivores have eyes that allow them to see virtually 360 degrees, but this does not allow for very good depth perception. But depth perception isn't such a big deal if all you're looking for is some grass. Depth perception isn't such a big deal because if you notice the owl, you don't care how far away it is. If you notice the owl and you're a tasty little mouse, you're going to just get out of there as quick as you can. But just keep this in mind that mice and many other herbivores do definitely have lateral facing eyes. So if they want to get a good look at you, or if they want to look at something, they're not going to do this. They're going to do this. So the next time you see like a pigeon or something turn its head like that, that just means it's noticed you and now it's interested in what you're doing. I mentioned before that humans, in comparison to many other animals, have pretty good, clear vision. We have what's called a good visual acuity. So the sharpness of our perception is superior compared to most animals. But we're definitely not the best. Eagle vision, for example, eagles have a kind of vision that's 8 times sharper than ours. So that basically means they can see about 8 times further. So that's why if you're an eagle perched up on a cliff, that's why you're able to see, that little mouse down there in the valley and know exactly how far away it is. The part of your visual field that you have the most acuity in is your central vision. The most center part of that would be called the fovea. So this is your area of your highest visual acuity. It's at the center of your retina. Outside your central vision, there you have your peripheral vision, which is relatively poor visual acuity. Now, different kinds of animals have different kinds of eyes. I'm sure you've noticed that if you look at various kinds of insects and various kinds of, other animals, that their eyes don't really look like ours sometimes. So there's 4 basic kinds of eyes that you can have. The most basic kind would be called pigment spots or pit eyes. These allow for only a basic sensitivity to light. It looks like just a discolored patch of skin, like a dark area of skin. So that just allows the animal to detect there's light somewhere in this direction. A more complex kind of eye would be called the simple eye. So the simple eye is basically when you just put a bubble on top of that pigment spot. So now we have very excellent light detection because the light will kind of go and enter that bubble and get trapped, but still very poor visual acuity. So the animal is very good at detecting light, they just don't really know anything about it. Like they probably don't really understand where it's coming from or what it means. But then you get to humans, and many other animals have the same kind of eye as humans. What we have is called a camera eye. So a camera eye, the reason we call it a camera is because it has a lens, just like a camera has a lens. And that lens allows us to have excellent visual acuity. But then there's a 4th kind of eye that's very kind of complex and interesting kind. The best example of this that you can find would be on a fly. So if you go take a really close look at a fly, you'll see that their eyes, they don't have 2 eyes. They have thousands of eyes, actually. They have all these tiny little bubbles. It looks like massive amounts of simple eyes just all over their head. So that's basically what this is. That's basically how it works. They have tons of tiny little independent eyes pointed in all these different directions. And depending on the patterns of activity of all these different eyes, they'll be able to tell exactly where different things are in their environment. And because because each one of these little eyes overlap with its neighbors, there's a massive amount of overlap in that visual information. And because there's so much overlap, this allows the fly to process that information super fast, and that's why it's really hard to, swat a fly, because to the fly, you're basically moving in slow motion. I mentioned that humans have camera eyes. So the camera eye consists of a few important structures, not just the lens. The colorful circular part, that would be the iris. And then the hole in the iris, the black part, is the pupil. And that is just a hole. There's nothing there. That's why if you go to the optometrist, they can hold up that, light emitting tool and look into your eye through that pupil. So the iris is just a colored circular muscle that can expand and contract to let different amounts of light into the eye. Now, once the light enters the eye, or once the light hits the eye, it's going to pass through two different structures that will redirect that light into the eye. So the outermost part is the cornea. The cornea is on the very, very tip of the eye. Like if you look very closely, you'll see a tiny little bump at the front of my eye. And that tiny little bump, or that tiny little bubble, is this transparent membrane that will bend light rays. And is that structure I've already mentioned a few times that helps to redirect the light. The entire inside of your eye is covered with the photoreceptors, the transducers of vision. These are called the retina. So it's just a layer that covers almost the complete inside of your eye. There's only one major exception, and that is where the optic nerve meets the eyeball. At that point, we have the blind spot, which we talked about last time. Remember when I was doing this? Yeah, that hole right there, that's where your blind spot is in your eye. There's some important differences between your two kinds of photoreceptors. So in this retina, you have rods and cones. Now, the vast majority of these photoreceptors are rods. Rods, you have about 120 million of them in each eye. These are your photoreceptors for just like light and dark, so how bright is something. Rods don't allow you to see color, and you find them mostly in your peripheral vision. Cones, on the other hand, you only have about 5 million. These allow you to see color, and they're mostly found in your central vision. So what I'm saying is, your ability to perceive color is most accurate. Your ability to perceive color is best in your central vision. So whatever you're directly looking at, you'll have the best sense of acuity and your best sense of color. So when we talk about the peripheral vision, everything you're not looking at, if it looks very colorful, if it looks very detailed, that's just another example of your perceptual system being creative and filling in those blanks. In reality, all these colors you see out here aren't really there to the extent that you think they are. But before we talk about color, let's just talk about brightness. So your perception of brightness, that's conducted by those rod cells. And the way it works is through the use of rhodopsin. Rhodopsin is this light-sensitive pigment that you find in the rods. So as the rods are exposed to more light, this pigment will get depleted, and then once you put yourself in a dark room, that pigment will start to build back up again and become more sensitive. So the longer you sit in the dark, the more this pigment will build up and the more sensitive you'll become. So that's how darkness adaptation works. It's just you start to build up more and more of this pigment, allowing you to see better in a dark environment. Now, once you've been sitting in the darkness for about 10 minutes, that's when your rods are going to become more sensitive than your cones. And once you've been sitting in the dark for about 25 minutes, that's when you reach your peak of sensitivity. So if you want to have excellent night vision, you should just wait for about 25 minutes in a dark room, and then you'll be good to go. Waiting any longer than that is just going to be a waste of time. So here's a few illusions that I'd like to show you. This first illusion is called mock bands. And mock bands you find them all over the place. You see them every single day, and your brain just kind of automatically filters them out. You don't notice them, but they're definitely there, and they definitely produce an illusion. So here's how the illusion works. If you look closely at the border between two of these bars, you might notice that that border kind of seems to be a gradual change in brightness. So like look at the two center bars. the one on the left, the one in the center on the left, the darker side, I would say, looks like the right side, and the brighter side looks like the left. In other words, it looks like it's going from lighter to slightly darker. And that pattern is repeated for every single bar. So every single bar looks like it's lighter on the left and darker on the right. It's almost like it's kind of like a scalloped kind of brightness curve. But that slight little gradual change in brightness doesn't exist. It's purely perceptual, and that's the result of you trying to use the context to figure out the relative brightness of these bands. And I can make it clear that this is an illusion by simply changing the context. So once I separate the bars, now you can clearly see that they are uniformly shaded. So the most classic example of mock bands in action is just mountain ranges. The next time you go outside and you look at the mountains, you'll probably notice that they look much darker on the peaks. They look much darker at the top than they do at the bottom. And that's not simply due to mock bands, but mock bands definitely contributes to that perceptual experience. But if you don't believe me, if you don't see what I'm talking about here, here's one more example. And I think this is a really cool example. I didn't create this illustration. I'll give some credit in the comments down below, but I just wanted to include this picture because this is a very clear example of how you perceive the relative brightness of objects based on context. So once I start removing that context, you'll probably notice that these two patches, A and B, are starting to look a little bit more similar. They still don't look similar yet, but they're getting there. So it's not until I remove that tiny little last bit of context that now you can make the argument that yes, they are definitely the same. So you virtually have to remove all the context to get at the actual brightness of these objects. And here's another one that I made. So with this one, this is called dynamic luminance because if you move forward or move back, it kind of looks like it's expanding and contracting. But this is also an example of how the context affects your perception of brightness. So when you look at the very center, it probably looks much brighter than it does on the outside border. And many students actually, when they look at the center, it kind of looks painful. It kind of hurts to look at the center. It's almost like you're looking at the sun. Well, that pain is purely illusory. There's no reason that the center should hurt you any more than the outside should hurt you because this screen can only be so bright. Right? I can't make the center of the screen any brighter, any whiter than any other part of the screen. So the whiteness is uniform all throughout, and if the center seems any brighter, that's purely because of the context. And I can make that very clear by degrading the context. So as you see, once the context starts getting more and more degraded, it starts becoming obvious that this was just a contextual-based illusion. So let's know about brightness. Now I wanted to just mention a few things about color perception. Remember, color perception is conducted mostly by cone cells. And there's two basic theories regarding how we perceive color. So you have the trichromatic theory, which argues that we have three cone types. You have red cones, blue cones, and green cones. And it's the combined activity of these three kinds of cones that allow you to perceive all the different colors of the rainbow. But then there's a second theory called the opponent process theory, which argues that we have three color vision systems. So we have a red-green system, a blue-yellow system, and a bright-dark system. So it's the combined activity of these three systems that allow us to perceive all the different colors. Now it's that second theory, the opponent process theory, that seems to have more support from the recent research. What I'm saying is, if you remember that example of perceptual adaptation from that previous video, if you remember how that works, well, basically you adapt to some image. So while I'm talking, I'm going to have an image on the screen, and I just want you to look at it. You need to keep your eyes still. Just keep looking at one particular part. Let me just remind you that perceptual adaptation works by your eyes becoming accustomed to constant unchanging stimuli over time. And the consequence of this adaptation is that you perceive a negative after effect. You perceive the opposite of what you adapted to. In this case, you're perceiving the opposite colors. So the fact that you can have opposite colors seems to support the fact that we have this opponent process theory where each color is paired with its opposite. So here's another example. For this one, just stare at the dot in the center, and while I'm talking, you are adapting. But in just a moment, I'm going to remove this, and you're going to see a grayscale image, but it's not going to look grayscale. The after image, though, of seeing a regularly colored picture probably faded pretty fast. And here's one more. With this one, you see all these different colorful splotches, right? Once again, just look at that little dot in the center. But the thing about this one is, the longer that you look, and if you can keep your eyes really still, you'll start to notice that different kinds of colors are going to start fading away. It's different from time to time, but you might notice that, like the blue ones disappear first, and then the purple ones go second, and the yellow ones are third. And finally, if you can stare long enough and keep your eyes still enough, you'll get all of the colors to disappear, and all you'll be looking at that point is just a blank gray screen. The last thing I have to say about color is that there is some variance in different people regarding their perception of color. So some people can see color perfectly fine, but other people have color blindness or color weakness. So color blindness refers to your complete inability to perceive color. This is pretty rare. This means that you either don't have any cones or your cones just don't work. It's much more likely that if you have some color vision problem, it's color weakness. So you have an inability to distinguish certain colors. Now, red-green color weakness is most common, and it's much more common amongst men than women. Now, we can test to see if you have a color blindness or color weakness using what's called the Ishihara Test. So these images I'm about to show you, I didn't develop these. These are standard kinds of plates from the Ishihara Test. So I just wanted to show these to you to give me an example of what it's like to take such a test. If you fail the test, don't worry about it. Having a color weakness doesn't make you a bad person or anything like that. But if you do fail this test, then maybe you should go see your optometrist. So here's the first plate. So the way this test works is I just show you a plate that looks something like this, and you're supposed to try to figure out what's in this image. So if you can see it, in this example, it's the number 12. So that was easy, right? Hopefully you were able to do that one. If you didn't do that one, I have bad news for you. So here's one that's a little bit more difficult. So this is medium difficulty here. So in this one, you should be able to see the number 2. Sometimes people will report seeing the number 8. If you see an 8, that's probably a sign of a color weakness. And now here's a really hard one. Just take a moment to look at this and try to figure out what you see here. Do you see a 71? Or do you see a 24? Or do you see some combination of these? Now, if you see a 21, that's a trick. That indicates that you probably have a color weakness if you see a 21. What you should be able to see if you have absolutely no color vision problems is a 74. So that one was a little tricky. Now, we can also do this test with children. But with children, they probably don't really know their numbers very well yet, or they probably have trouble, identifying certain characters. So instead, with children, we just have them trace a line. So here's what the Ishihara test would look like for a child. All right? So that's it for your basic vision stuff. Next time, we'll go into more detail about specific topics within visual perception.